This work is directed by Dr. Jameson Rodriguez and co-directed by Dr. Gabriel Gomez. And this work is based on one of the Veronica's paper, the complete Maxwell-Proca theory. And well, this is the content of my presentation. And well, I'm going to start with the introduction. I want to start with the Patos allegory of the cave. Some of us have heard about it, and I think it's interesting because we have a group of people at the end of the cave, and all what they can see is the shadows projected on the wall. But one day, one of those men can go out of the cave and see the world as we know it, see the nature, and he realized that the reality is different about in comparison what he knew. So arises a question: what is reality? So philosophers base their answers in two concepts. One is the doxa, and the other one is the idea. But we can base our answers in those concepts because they're based on senses. So that's not enough nowadays. In the scientific community, we have the math language, and all our answers are based on the mathematical language. So, so if we take this to the physical, what we really want to know is how can I identify a physical system, right? So there are some requirements, and the first one is the avoidance of instabilities. And we have two important instabilities. One of these is the ghost in the Lagrangian theories, and the other one is the Ostrogradsky instabilities. Both conduce, both leads to energy problems, and we want to avoid them. And the other requirement is that we have to guarantee the correct propagation of the number of degrees of freedom. At this point, we have another question. How can we guarantee that? And how can we know what is the correct number of degrees of freedom for a specific theory? So at this point, we have the spin statistics theorem. With this theorem, we can identify bosons from fermions, and also we have a relation between spin and statistics of a specific particle. But we also have an equation which correlate the number of degrees of freedom and the spin of the particle. With this expression applied to the Maxwell-Proca theory, we have that Maxwell fields propagate 2 degrees of freedom and Proca fields propagate 3 degrees of freedom. So if both fields have the same spin, why they propagate different number of degrees of freedom? So to answer that, we have to take into account the invariances. So we have two important invariances for the Maxwell-Proca theory. The first one is the Poincaré group. Here, this one allows us to identify the kind of particle which we are working. And also this classification is take place because we have two important characteristics: the mass of the particle and the spin, and those are related with the Casimir invariance, two Casimir invariants. And the Maxwell and Proca fields are invariant under the Poincaré group. And the other important invariance is the U1 group. Here we have the gauge transformation, and if we apply this transformation to Maxwell and to Proca Lagrange, sorry, Lagrangians, we have that Maxwell is invariant under gauge transformation, but Proca don't. So it's not invariant. Sorry, it's not invariant under the gauge transformation. So that is the difference due to this invariant in Maxwell and not invariant under in Proca. We have an extra degree of freedom propagated by Proca fields. And now, well, at this point, we know how many degrees of freedom have to propagate the theory, but in the Maxwell-Proca theory, we have that it's not just the dynamic involved, but also the interaction between the fields, so that we have to guarantee that these interactions don't introduce more unphysical degrees of freedom, so that we use the Dirac algorithm. So we have to start at the primary level in the Lagrangian formalism, and we start with the equations of motion. These equations, those equations can be rewritten as this expression, where we have the Hessian at the primary level and a term called alpha. So as we want to avoid the Ostrogatsky instability, we find the first, the primary condition over the Hessian, and this is the primary degeneracy condition. And as we know that we don't have just equations of motion, but also it includes the constraints and physical degrees of freedom, we have to separate those different equations. So we have to introduce some definitions. The first one is the gamma vectors, and they are defined by this way, with the gamma vectors have to satisfy those conditions, and the other one is the auxiliary matrix. This is, well, in my opinion, this is the heart of the work, the heart of this work, and I want you to understand a really good why. So that I prepared this diagram. We are going to start. We are going to start with 4n plus m number of equations of this form. So we are going to associate each of these balls with each equation, right? And we have that the blue balls correspond to the Proca equations, and the other ones corresponding to Maxwell equations. So we introduce our auxiliary matrix, right? This allows us to split the equations into the different three kinds that we have. So we have three different groups. The first one is the Euler-Lagrange equations. We have 3n plus m Euler-Lagrange equations of this form, where the auxiliary matrix is introduced. Well, that's our dynamical degrees of freedom. And the other two groups, the second group is associated with the n identities of these forms, and those identities are associated with the Maxwell fields, and the last one is the m constraints associated with Proca fields.
Those 5 minutes.
Okay. Those relations, those constraints and identities are of this form, and then we pass to the next level and we repeat the same procedure. So we at secondary level, we have to guarantee the constraints hold true all the time, so that we find or we arrive to the secondary level equations of motion, and we get the secondary degeneracy condition. This is the form, and After that, we have to define again the respective gamma vector and auxiliary matrix of that level, the secondary level, and guarantee the evolution time of these constraints. Those are the secondary Lagrangian constraints. We have the third level that correspond the Euler-Lagrange equations of this level. As I summarize, we have this image, and we have that the number of Euler-Lagrange equations that we have at each level. The identities, gauge and Bianchi identities, that's just for Maxwell fields at primary level. And finally, the constraints that we find and each level. And we realized that there is a pattern in the form of the alpha and Hessian terms, and we compact this pattern into those equations, those expressions, and well, these expressions can be used, but we have to take care because they don't have the space-time index, and this is just supported to know what we have to find with my calculus, and not a solver tool. And well, then we have the relation of our Lagrangian equations and our Lagrangian constraints. We have the counterpart in the Hamiltonian formalism. So we have this restriction, and we have a group of n plus n equations of the independent, and those led to the primary Hamiltonian constraints of this form. And we can correlate these primary Hamiltonian constraints with the Lagrangian quantities of this form. And if we demand that this evolve of the primary Hamiltonian constraint should be equal to 0, we recover the identities and the constraints, Lagrangian constraints, primary Lagrangian constraints. And at the same time, this evolution of time of the primary Hamiltonian constraints led to the second group that correspond to the secondary Hamiltonian constraints. And those also is a group of n plus m, and we have done that the evolution of these constraints conduce m of these equations conduce to the relation with this Lagrangian quantity, and demanded that should be equal to 0. We recover the secondary Lagrangian constraints, and with our group of primary and secondary constraints, we pass to classify them into first class and second class constraints, and we support that in the Poisson bracket. So if the constraints weakly vanishing Poisson bracket with all have a weakly vanishing Poisson bracket with all the Dirac constraints, there are their first class. Otherwise, we have second class constraints. So that we have as a result this classification, and we have a 2m first class constraints and 2m second class constraints. With these results, we finally pass to the counting of degrees of freedom, and we have two equations. One is related with the Lagrangian parameters, and the other one is related with the constraints in the Hamiltonian formalism. So we can establish a connection between these quantities and the first and second class constraints. The first one is the Lagrangian constraints, and it's equal to the number of the first class constraints and second class constraints in the Hamiltonian formalisms minus the first class primary constraints. The gauge identities is equal just to the first class primary constraints, and the last one, the gauge parameters, is equal to the first class constraints. So by both ways, we arrive to the same result, the same answer. So we have that the degrees of freedom propagated by the Maxwell-Proca theory is equal to 2n plus 3m. So that means that Maxwell is propagating 2 degrees of freedom and Proca is propagating 3 degrees of freedom. And finally, the conclusions of this work, we have that the main conclusion of this work is the possibility to remove the non-physical degrees of freedom and guarantee that the theory is a healthy theory free of instabilities and guaranteeing the correct propagation of the number of degrees of freedom. Also, we find the necessary conditions over the Hessian, the degeneracy conditions over the Hessians, and we find the number of constraints necessary to guarantee the correct number of degrees of freedom and avoid pathologies in the theory. So that's all.